And so when we're doing these Punnett squares, we're doing these analyses and predicting the outcomes of these crosses. If you're an animal breeder, you want to know what the ratios are going to be of the offspring that you have so that you can figure out what it is that you're going to be working with in your next round of animals. So that's the reason that we assign these letters, these combination of letter symbols, to the different variants of these genes. Generally, we use uppercase and lowercase, but sometimes genetics are a little bit more complicated than that. In fact, a lot of times they're more complicated than that. So if we don't know what the genotype is, we can always put down if they are a pigmented individual, like in the case of albinoism. We can write a big A, but we don't know whether they are big A, or big A, little a, because they look like the dominant color, but they could have that recessive gene lurking around in the background. So you can put a placeholder for the second letter if there's an identity that you can't be certain of unless you do a gene testing. And so here's an example of how that happens, looking at the Punnett square for this. So if we have a mother that is albino, she has to be homozygous, little a for albinoism. And so her gametes are all going to have little a's in them. So we always put the mother up here on the top, and we always put the father down here. So if we cross an albino with a pigmented individual, the father is going to be, in this case, homozygous dominant, so big A, then what you will see in the offspring is big A and a little a for all of them. Because you know that the father is giving a big A and always a big A to all of his gametes, to all of his sperm, and you know that the mother is giving a little a to all of her gametes, to all of her eggs. So what we would say is that the genotype of the offspring between pigmented homozygous father and albino homozygous mother, all of them big A, little a, big A, little a, big A, little a, big A, little a. So they all have the genotype big A, little a, and they are all pigmented. Now, where it starts to get interesting is when these guys go out and start breeding in the population, because if we have these individuals, if you have a mother that is big A, little a, and you have a father that is big A, little a, what you end up with in the offspring is just like we saw in the picture of the family. We've got offspring that's the homozygous dominant. You've got this one that is heterozygous and dominant. It has the dominance for the pigment. You've got this offspring that's got dominance for the pigment. So 1/4 of them are going to be big A, 2/4 of them, or half of them, are going to be heterozygous, big A, little a. And then we've got this one albino guy that pops up here in the end. And that's how you know at some point there had to have been an albino parent somewhere in the background. Because 3/4 of these offspring are going to be pigmented, and 1/4 of them are going to be albino. So that's why it's so interesting, like if you've ever seen the American Kennel Club, the pedigreed dogs, where you can trace their lineage back a long way, and you know who the parents and the grandparents and the great-grandparents. You can look at true breeding dogs. You can do this with lots of different pets. They do this to make interesting colors of reptiles. When I was a kid, I was really into snakes, and so I used to go to snake shows, and you would see what would happen when they'd put together like all of these parents that had these like crazy genetic variations, and they'd come up with these offspring. When we look at the betta fish, you're going to see that as well. The bettas definitely have new and really interesting variations because of the way that we've artificially selected for the characteristics that we want. So it's really cool to see how this all works its way through the gene pool. And one of the things that you have to realize about this is that there has to be an albino mother somewhere in the, or an albino parent, not necessarily the mom, but an albino parent somewhere in the past in order for this to show up in the future. Because unless this was a mutation, there has to be a parent passing along that trait to the offspring. It has to have come from somewhere. You can't will yourself to get different genes. You can't say, oh, I would like to have the genes for albinoism, so I'll pass that along. It has to be there somewhere, or it has to be introduced through a mutation. So what we look at next is the probability and chance playing a central role in genetics. So if you've ever done any kind of game with dice, you know that you shake them up, and then there is equal probabilities that you could get any one of those. Is it 6 by 1? So any of those 12 chances in the shake of the dice. So chance is important in genetics, and probability has a central role for two reasons. The first is the consequence of segregation, where we talked about the chromosomes separating and going into the different eggs and the different sperms. So there's a chance that you could get one of the alleles or the other one from your mom and from your dad. And the second reason is that fertilization is also a chance event. So it's like rolling the dice twice. We have once when the alleles are separating to go into the different eggs, and we've got another chance when the egg and sperm are coming together.